Sample problem 18.8. The equilibrium constant Kp for the reaction N2O4 gas is converted into NO2 gas is 0.113 at 298 Kelvin, which corresponds to a standard free energy change of 5.4 kilojoules per mole. That's a positive value, by the way. In a certain experiment, the initial pressures of N2O4 are 0.53 atmospheres, and for NO2, 0.122 atmospheres. Calculate delta G for the reaction at these pressures and predict the direction in which the reaction will proceed spontaneously to establish equilibrium. Okay? So this is the idea that we may not be at equilibrium. We're not under standard conditions is the main point. So if we're under non-standard conditions, it can be shown that the change in free energy for the system is equal to the standard free energy for the system. That's the degree sign, standard, plus RT ln Q, where Q is the reaction quotient. It's an adjustment factor. So the free energy change is different if we're under non-standard conditions. Okay? So in this particular problem, they tell us what the standard free energy change is. It's 5.4 kilojoules per mole. So we've got that. Let's just make sure we get the sign right. So we just need to add the correction term, RTLNQ. So we're told that this is happening at 298 Kelvin. So we're going to add to that the value of R. Remember, R, when we're doing energy calculations, thermochemical or thermodynamic calculations, we use the 8.314, not the 0.08206. The temperature here at this particular problem is, well, it's the same. It's 298 Kelvin. And then we're going to multiply that by the natural log of Q. But we've got to figure out what Q is. So Q, if you remember, is the reaction quotient. Way back from equilibrium, right? So that's the concentrations or pressures of the products. So QP, if we want to call it that, would be the pressure of NO2 squared divided by the pressure of N2O4. And those are given. So the pressure of NO2 is 0.122 atmospheres. Remember that we don't put the atmospheres in when we're calculating reaction quotients or equilibrium constants. And the pressure of N2O4 is 0.453. Right? Products over reactants. So 0.122 squared divided by 0.453. Okay? So that is 0.0329. 0.0329. So this would be the natural log of 0.0329. Okay? So what I'm going to do is I'm going to figure out this second term, 0.0329. Okay, so let's just go ahead and go backwards. Let's take the natural log of that, multiply that by the 298, and then multiply that by the 8.314. And you get negative 8462. Now here's the issue. So let me bring it back down here. Was it 8362 or 8462? 8462. And what were the units? Joules per mole, right? See how those are not in the same units? You cannot add or subtract numbers if they're not in the same units. So what I'm going to do is I'm going to put them both into kilojoules. So for this second term, I'm just going to say it's a kilojoule per 1,000 joules. And then that will make it 5.4 kilojoules per mole. Minus, right, because you have this minus right here, 8.46 kilojoules per mole. Okay? So what you get is minus 3.06 kilojoules per mole. Now here's the significance of this calculation, which is very powerful. What it says is that for this reaction under standard conditions, delta G is positive, delta G is 0 is positive. That means that it's non-spontaneous under normal conditions, under standard conditions. However, under these conditions, where the reaction quotient is less than 1, think about Le Chatelier's principle. What does Le Chatelier's principle say? It says that if Q is less than K, the reaction will move towards the products. Now we have a connection between energetics and equilibrium. Essentially what's happening is, because Q is less than K, delta G is less than delta G naught, right? K in this problem is given as 0.113. Q is only 0.0329, so Q is less than K. Delta G 0, or delta G naught, is 5.4, positive, but delta G is negative, negative 3.06. So the driving force behind chemical equilibrium is really energetics. The fact that delta G is negative means this reaction will move toward the products. N2O4 will start forming more NO2 until it comes to equilibrium, and then delta G will equal delta G naught. At some point it becomes non-spontaneous. Okay? So the key to this, or the take-home from this, is that we can explain equilibrium in terms of energetics, delta G.